So I'm seeing about two different answers here. Either cosine squared or 1. So let's figure out what it is here. So the top is cosine. We're going to leave this cosine. The bottom is secant, which is equivalent to 1 over cosine, right? With a fraction and a fraction, we learned yesterday that we keep, change, flip. We keep the top, we change the multiplication, and we flip the bottom. So it becomes cosine over 1. Well, then this just becomes cosine times cosine, which is cosine squared. So that is the correct answer of cosine squared. Be our single trig function. Like I said, we're going to be practicing this more today, except adding some more layers to it. And we'll be doing this for the next few days. This is the last major trig thing that we're going to do. It'll take a few days, like I said, but this might seem a little bit difficult. I'm not going to say that this is going to be easy. It will require you to definitely use your brains here. So we're going to be establishing, as the book calls it, establishing trig identities today. You can think of that word as basically proving trig identities today. Okay, so we're going to start with a few. We're going to make a big list of trig identities. Think of these as tools you're going to use to do proofs. So if you think a little bit back to geometry when you had to do proofs, this isn't going to be exactly the same as that, but it's the idea that you're going to already know something is true, and you're going to have to prove that it's true using trig identities. We'll add to the list that you made yesterday. If you wrote them down yesterday, great. If you want to rewrite them, you can. I would probably rewrite them in a separate list. But we're going to be adding a bunch more as well. So I'll let you stay.
What was the title on the first slide, please?
Oh, sure. 7.4 trig identities. So we're going to start our first list. We're going to call these the reciprocal and quotient identities. The name of them isn't really that important, but that's what they're classified as. And these are several of them are going to be the same ones you used yesterday. So the first one, the cosecant of theta, is 1 over the sine of theta. One you used yesterday a lot. Hopefully that one's familiar. Shouldn't have to struggle with too much that one. And then we also have the secant of theta. Secant is 1 over cosine. 7.1. And this one you didn't write down yesterday, but it doesn't hurt to write this. Just another way of stating the cotangent. The cotangent is also 1 over tangent. We don't use that a whole lot, but it is a reciprocal identity. Because if you flip something, that's reciprocal. And then the other two that we used yesterday, where the tangent is the sine over the cosine. Use that one a lot. And then the cotangent, which is reciprocal of that. Cotangent is cosine over sine. So like I said, all of these you should be pretty familiar with. Shouldn't be the first time you've seen any of these. And hopefully you don't have to look at the list in order to know these. There's a quote from the book that I'm going to read because I thought was a little entertaining. That's not meant to be entertaining, but you guys will get out of this. So in your book, it has a bunch of trig identities listed. It has these 5 and then about 10 other ones that we're going to be adding in just a minute. And it says this list comprises what should be referred to as the basic trigonometric identities. These identities should not merely be memorized, but should be known just as you know your name rather than have them memorized. So I'm saying that you should know these as well if you know your name. Obviously, this.
But we know our names because we memorized it when we were kids.
Right.
Because I know a lot of workers not going to write their names.
Yeah, there's like 10 more that we're gonna go over. Yeah.
I was
So that's what the book expects of you. I'm not gonna require that, but I'm sure you guys know that the tangent is sine over cosine as well as you know your name. Not merely memorize them, but know them. So that's the goal, is to know this as well as you know your name. This next identity, I'm going to actually do a little kind of a proof how this came to be here. It's called the Pythagorean identity. You can choose to write this or not if you just want to watch. It's fine. But I'm just going to prove to you how we came up with this, and then we'll add it to our list too. So the Pythagorean identity is kind of an important one, and it comes from obviously the Pythagorean theorem. Right? So show you what this is, where it comes from. If I were to draw, think back to the unit circle. From the unit circle, anybody remember what the distance from the middle to the outside at any point, the radius? What is the radius? What is the radius of the circle? If this is a perfect unit circle, yeah, the radius is 1. So anywhere I draw from the middle to the outside is 1. All of these, the radius is 1. Radius is any place, the radius is 1. Okay, so if I were to draw this radius here, I know that's 1. And then I were to make a triangle out of this radius. Yes, a triangle. And this is a right triangle. So this triangle has a hypotenuse of 1. Okay, how could we classify, what could we call this side? Okay, it would be adjacent, you're right. In terms of a variable, even better than A, even better than B. So keep in mind this is on a coordinate plane, right? X. Yeah, this would be the x distance, right? Okay. You guys agree with that? All right, that's x. Because this is moving, remember, this is the origin on the unit circle, so this is an x distance, right? And then what would this side be? That'd be the y. That's the height, right? That's how much we're going up. Okay. So we get a triangle. This triangle is an x, y, and 1 triangle. The Pythagorean theorem says that a squared plus b squared is c squared, right? So we can write that as x squared plus y squared equals 1 squared. Right? This is the right triangle. Okay. So let's take another thing that we know. With the unit circle, we know that x equals what? Oh, well, at 45 degrees, it would be 552. But I'm just saying that this doesn't have to be a 45. But x is equivalent to one of the trig functions. X is cosine, right? Yeah, cosine, right? So x is the cosine of theta. And then y is, right. So then what we could do, take the fact that we know this, if this is x squared, we could write that as the cosine squared. Okay. And y is sine, so that would be plus sine squared. 1 squared is just 1. And this is what we call the Pythagorean identity. It's used a lot for these, like a trigonometric proof or a trig identity proving something. This fact that the cosine squared plus the sine squared equals 1. And oftentimes this is written in different ways. You'll see it written like this: sine squared plus cosine squared. That's generally the way that we write it. For whatever reason, we just write sine in front of cosine. But it's the same thing, you just switch them around. You could also, if you wanted to know what cosine squared was, well, cosine squared is the same thing as 1 minus sine squared. I just rearrange that equation, right? And I could also say that sine squared is equivalent to 1 minus cosine squared, right? So there's a bunch of different ways that you can write this identity here. This is an identity. You can write it a bunch of different ways. This is true, this is true. So when we're doing these, we're going to need to maybe sometimes even rearrange these equations a little bit to make them fit whatever we want them to fit. So that is called the Pythagorean identity. Now there's also a couple other ones. Here's a joke that goes along with this Pythagorean identity here. It says, I wish I were a sine squared and you were a cosine squared, so that together we would be 1. You get it? So this you could use this as a pickup line, right? You know a math geek, right?
I could take one.
We have to know the Pythagorean identity. I got more laugh though. I did not come up with this joke, but I thought it was good. Crowds. You guys get it, right?
You know my math a lot more than her.
Alright.
Takes too much brain power to think about it.
You get trying to like, make sure we understood.
But it takes a certain amount of brain power to understand the joke. It makes it be awesome. But
At least I got a reaction out of it. Alright, so this is our first one of, there's actually 3 Pythagorean identities you're going to write down. This is probably the most important one that you'll use the most. Sine squared plus cosine squared is 1. You might remember it now. Remembering that joke, right? Yeah. So you don't have to memorize these, but if you were going to memorize one, I would say memorize this one. The other 2 are a little bit harder to memorize because they're not as familiar of trig functions and they're not used as often. But tangent squared theta plus 1 equals secant squared theta. You can also rearrange this one. We don't write every single way you can rearrange it because that would just be too much. But you could rearrange this. You could also say that 1 equals secant squared theta minus tan squared theta. Would be one way of writing that. You could also rearrange it and say that tan squared theta equals secant squared theta minus 1. So there's all kinds of different ways you can rearrange these equations to make them fit whatever way you need them to fit. Just using a little algebra. And the third one, cotangent squared theta plus 1 equals cosecant squared theta. And again, this one could be rearranged. You could subtract the cotangent squared over, or you could just switch their spots. Cotangent squared would be equal to cosecant squared minus 1. Rearrange that however it's needed. And you don't have to memorize these, but have that list so when you do problems, we're going to be doing problems here shortly, and you can refer to this list. And we got one more set we're going to add. These are called even and odd identities. These tell us what to do if we have a negative inside of these functions. We've got 6 of these because they're 6 trig functions. And I'll give a little explanation of why this is the case that it is. The first one, sine of negative theta, is the same thing as negative sine theta. And along with that, it pairs up with cosecant, because those are reciprocals. Cosecant of negative theta is negative cosecant of theta. So this is called an odd identity. For cosine, if we put in a negative theta into cosine, we actually get a positive cosine out. And same with secant, because that's reciprocal. Secant of negative theta is positive secant theta. You don't have to understand these, why they are the way they are, but I'll give you just a little explanation. Maybe this will make sense. If not, don't worry about it. But if you think back to sine, the graph of sine looks like this. It goes this way. Okay. So sine is an odd function. If you notice, like on both sides of the axis, they're kind of going opposites. This side goes up, right? Going up, and this side's going down. So like if, for instance, if I have 1, if I looked at 1, the value here would be, whatever, sine of 1, or whatever it is. Well, if I went in the negative direction, it would be just the opposite, right? It would be the same thing, except the opposite sign would be like the negative y. So the positive x gives you the positive y, and the negative of that gives you the same value except the negative. It's off, they're kind of opposites, right? But if I were to look at the cosine, it looks like this. It starts at the top, goes down this way. If I were to do the same thing with cosine, say right here, the positive 1 and the negative 1, they're actually the same y value. See, they're on the same level. If I were to go out here, they're the same y value. Here, they're the same y value. So whether it's a positive or negative that you plug into cosine, you actually get the same answer. Whereas sine and cosecant, if you plug in a negative, you get the opposite answer. You get a negative y value. So that's why this is the case. And you don't have to understand that just know this list, but if you're curious as to why that is, that's why that's the case. And then there's 2 more, the tangent and the cotangent. And they both, the negative sort of just pulls out in front. You put in a negative, you get a negative out in front of it. And the reason why for that is very similar. We haven't looked at the tangent graph, but the tangent graph, if you're curious, it's periodic as well, but it looks kind of like this. Just like repeats itself like this. And it's also odd, meaning that if you were to choose the same spot here and negative, there would be opposite signs. That's why that's the case. So that completes the list for now, these 6 right here. We're not going to use all of these today. You might not even ever use one of these, but just a list that you need to have because you might need to use it at some point. Just like a set of tools that you have, you can plug them in if you need to. Everybody good with this? So make sure you have that you can reference. We're going to go on to solving, if you will. We're going to call it establishing. The book refers to it as establishing the identity. You almost might say like prove the identity. It's the same thing. Your book just calls it establishing. So what we have is a true statement. Cosecant theta times cosine theta equals cotangent theta. That's a fact. Okay. So we're not solving anything. What we're going to try to do is to prove that this is true. Prove cosecant times cosine is the same as cotangent. How we're going to do that, this is what we're going to do here, is we're going to try to show that the left side equals the right side. How we're going to establish it. We're going to somehow replace things on this left side until it equals the right side. Okay? We want to make the left side equal to cotangent. If we can make this look the same as that, then we'll prove that they're equal. That's our goal. Yesterday, when you did this, you just replaced everything with sines and cosine and simplified it, which is basically what we're doing. We're just taking this left side and we're saying that we want to simplify it to a single trig function, but we already know what that answer should be. That answer should be cotangent of theta. So we need to manipulate this side until we end up with that. So who has an idea? What could we do to this left side to get some way there?
Could you make cosecant 1 over sine.
That'd be a good start. Yep. We're going to replace cosecant with its reciprocal, which is 1 over sine of theta. It is important that you show your work on this because we already know that the thing is true, right? So we're going to have to show that we know, show how we know it's true. Very important that you show your steps. If you just write the answer, cotangent theta equals cotangent theta, we haven't done anything. We got to do that. We write out the whole thing. Right? So we've done that. That's good. Now, if we were to multiply this would then just go to the top, right? So we just do the same thing as cosine theta over sine theta. You should write this intermediate step, even if you know what's going to happen. You should write it because this is a proof. Don't skip steps on this, even if you can do things in your head. Write that step. You need to show that you plugged in 1 over sine theta in for cosecant. Don't just skip straight to this step because then if someone were to look at your proof, well, they wouldn't know how you got from here to here. All right, now what is cosine over sine? Yeah, it's cotangent. That's what we're trying to prove, right? This is cotangent. So cotangent theta equals. That's it. We proved it. We proved the left side equals the right side. Sometimes in like geometry, you might have even had a teacher that would do like, if we had a teacher that would do that. You can do that if you want to, but it's kind of a proof, but it's kind of just proving an identity, but you wanted to. Okay, that's it. We've showed the left side equal the right side. Okay, let's try a little bit harder one. You never really know if it's going to be an easy or hard one. Sometimes it looks like it should be super simple, and you make one substitution. Sometimes not so much. There also isn't one right way that, like, there isn't this equal set of steps you're always going to do to solve it. So you kind of got to use your brain a little bit. Look at all your list of substitutions you can make, and then use your brain to get there. You guys are going to have 3 or 4 problems like this to do on your own. I'm going to give you some time in class to do it. And each of the examples are going to match up with basically a problem in your book. So like the first example matches up with the way that you're going to solve it. You'll do a different substitution, but it'll all line up. So the second one, what do you guys think we probably want to do first here? We want to try to make this equal to secant. What should we do first? Okay, that's a good idea. That's based off of what you were doing yesterday. That's what you would want to do. The only problem is we got a negative there. Right? We do have some identities that we just wrote out with the negatives, right? So let's try to get rid of that negative because this one doesn't have a negative inside. So let's use that. Now it's not going to look exactly the same, but you can see here we said that the tangent of negative theta is the same thing as negative tan theta, right? So we do have to do a little bit of gymnastics here to get there, but I'll show you how this works. So let's just leave the 1 as 1 plus. Now this tangent squared of negative theta, is this the same thing as tangent of negative theta squared, or is it the same thing as tangent of negative theta squared? Which one of those is the correct way to write that? Yeah, the first one is correct. So if you remember with these trig functions, this squared kind of in the middle of these two means that the whole thing is squared. So this is the same thing as saying the tangent of negative theta quantity squared. Given that's the case, tangent of negative theta is just the same thing as negative tangent of theta, right? So that trig identity I just showed you, you can just sort of pull the negative in front. It's equivalent. And we're just gonna put the right side still. Make sure you carry that right side along with you. Even though you're not going to change the right side, make sure you write it every time. Now, if we square a negative tangent theta, what does that equal? Yeah, it makes it positive, right? The negative, when you square it, it makes it basically go away. It's -1 squared. And then tangent of theta squared would then just be actually the tangent squared of theta, which is like that. So, and it works out so that it ends up just being the same thing as tangent squared theta. We'll see this squared theta. And let's look at our Pythagorean identities, because this kind of looks like it could be a Pythagorean identity, right? 1 plus or minus something squared. Whenever you see something squared with a 1, generally it's going to be a Pythagorean identity that is either going to be written exactly or you might have to just rearrange it. This is one you can see that we wrote exactly right there. Tan squared theta plus 1. The only difference is these are in different, just change places here. Show you. Right, you're allowed to change this around 1 plus tan squared theta. It's the same thing. So we just rearrange those two terms, and that equals what we want, which is the secant squared theta. So now we can just write secant squared theta equals secant squared theta. Because we know that 1 plus tan squared equals secant squared. And now we've proved it. Now we're going to try one more together. And this last one will be the hardest one that we do. It's got some multiplications on it. Just like to write that one out. You will want to write these down because, like I said, the 3 problems that you're going to have to do match up with these, like the same steps you're going to do. You're going to make slightly different substitutions, but they're going to be the same steps. All right, so let's think about our options here. What do we want to do with this? How we're going to prove this left side, which looks way more complicated. How does that equal the cosecant? So at some point, we're going to have to do what with this? What's that? Yeah, not foiling, but distributing. Yeah, right, multiplying. So at some point, we're going to have to multiply that times this, right? That times both of those. Okay. We're going to have to do that at some point. Well, let's just think if we do that now, we're going to have cosine times tangent, which would be okay, and cosine times cotangent. That's okay, but it would be a little bit confusing. What if, before we do that though, let's just go ahead and change these. It wouldn't matter the order that you do this, but just kind of looking ahead, maybe it'll make it a little easier for you to do this. What could we write tangent as? It's the same. What's that the same thing as? Yeah, sine over cosine. Sine theta, cosine theta. And again, these first 2 steps are interchangeable. It doesn't matter which order you do them. So we're going to do that. Plus, and then what's cotangent? Cosine over sine. One thing that's different about these trig identities is it looks like we're making something more complicated. You have to make it more complicated before you can make it less complicated. All right, so now that we've done that, let's go ahead then and multiply this through. Both of those we got to distribute. I'm going to write out this step. You may be able to do this in your head, but it's a good idea to still just go ahead and write it out because it is I can prove. So this cosine gets multiplied by sine theta over cosine theta. Okay. And distribute plus cosine theta times cosine theta over sine theta equals cosine theta. So when we multiply this first one, what happens here? Yeah, cosines cancel. Good. So we're left with sine of theta. Let's make a little bit of progress there. All right, now with the second one, we can do this as cosine number 1 if you want to. So cosine times cosine equals what? Yep, cosine squared theta on top. And then the bottom is just sine of theta. Equals. So we just multiplied. Unfortunately, nothing cancels with this one. Now the next step, unless you've ever done this before, you probably wouldn't know what to do next. But when you have two fractions like this, the goal is generally to get them together into one fraction. You just want one fraction that maybe will simplify into something that fits again. So in order to combine these into a single fraction, we need the same denominator. It's the only way you can have fractions. This one currently has a denominator of 1, that one has a denominator of sine. To get them to combine, we need this to be the same denominator. So what we're going to do is multiply this first term by sine over sine. Because that's the same thing as multiplying it by 1. In the same way that if you were to add, you need to add, say, like a half plus, like a sixth. Right? If you were to add those two together, you would need to make this a sixth, right? And the 6 in the bottom. So you would multiply by 3 over 3. So you get 3/6 plus 1/6. It's the same idea, same concept, except we have trig functions, so it looks a little bit more. But that's the idea. We're just sort of getting a common denominator. So we're multiplying this by a number, or in this case, a function over itself. Because this is the same thing as just multiplying it by 1. So when we do that, we then have sine squared theta on top, and it's over 1, over sine of theta, plus cosine squared theta over sine theta equals cosecant theta. Alright, so we have the same denominator, which means we can now combine it into one single fraction. Since we have the same denominator, when you add fractions, you add the numerators and you keep the same denominator. So this is going to be sine squared theta plus cosine squared theta over sine theta equals cosine theta. We'll write that as one single fraction. All right, now what are we going to do? Yeah. Yeah, Pythagoras identity says that sine squared plus cosine squared is 1, right? So we can write this as 1 over sine theta equals cosecant theta. This whole top is just 1. Now we're almost there. What's our last step? What is 1 over sine? Cosecant, right? So cosecant theta equals good. So some of them can be a lot of steps like this one. Some of them might just be like one step to make one substitution. We'll practice these more and more over the next few days. But I do have 3 problems I want you to try. And like I said, each of those 3 problems matches up with these 3. So if you have your notes, you can just do the same type of steps. They're going to be a different thing you'll plug in, but you're going to do the same idea. So like your third question is going to be this. Your third question is going to be where you have to distribute, change, and then combine into a single fraction. So use these as a guide to help you until you develop the skills where you don't need that example necessarily. So your assignment is on Google Classroom, but it's going to be page 488. You're going to just be doing 22 to 26 evens. Okay. Yeah, I know, but Depending on how many we got through, I just wanted to modify like the answer. So if we got 3 of them, then assign the 3 problems.
I thought we were just doing all of the one page.
No, you don't have to do all of them. So they're also, I'll add it in here, but the page is up there on Google Classroom. Let me go ahead and change it here. It would be fun to see if I gave you all of them, how many people would come to school with all of them done. Yeah, so that would be kind of ridiculous if you had to do all those in one night, but especially these fraction ones. Oh, 400. So yeah, you just got to do these 3, 22, 24, and 26. 22, we actually did 21 in class, so I purposely a lot of times we'll do the odds. You can see these are very similar, right? 23 and 24 are very similar, so you're going to do the same strategy. And then we just did 25, which is very similar to 26, right? So use the same strategy until you figure out, how to do these better. You have a model. Now, it still might be a little challenging, but you're going to do the same type of steps. So use that model as you go in order to